Okay, here we are with TAD. We're going to take a look at High Altitude Survey Balloons by Sea Space Systems from 1963.
Sea Space Systems.
So, Sea Space Systems has developed a small balloon which can achieve altitudes up to 150,000 feet, carrying survey instrument payloads. This balloon utilizes the corporation's new balloon fabric, MERFAB. Because of its very light weight and high strength, MERFAB allows the construction of balloons with extreme altitude performance and cold temperature accommodation. Operational objectives of this survey balloon include launching ease, along with reasonable cost and good reliability. The new concept in launching is directed towards one-man operation in elevated winds. Recent flight experiences with the balloon and unique launching technique have indicated very satisfactory results. Well, that one man must be happy.
He must be in a very fast car on a runway in the right direction.
Yes, the high winds. Exactly. 150,000 feet is ridiculously high.
And that's is that going to be what is it, super pressure or a zero pressure balloon or a mix?
That's a good question.
It says it's high strength.
Yeah, that sounds like super pressure.
Extreme.
Yeah, it doesn't seem to mention like longevity. Well, let's find out.
Or it's just one of those that goes up and pops.
Could be.
I mean, it's what we've been doing for decades, so
Yeah,
I guess we shouldn't be surprised.
Right.
Mylar, probably applying 2 years ago in order to lighter fabrics.
Yeah, thinner films are necessarily rather weak. That's yeah.
Well, physics, you know.
So when they're talking about the loads that would be experienced in a flight from launch through the troposphere to altitudes of 150,000 feet, loads in quotes here are the the turbulence and buffeting wind shearing basically going through the jet stream. That
would be pretty rough.
Yeah, because
at some point you're cruising along and all of a sudden you're yanked away at
right.
I want to forget what the jet stream runs at.
Hundreds of miles an hour, 100 to 200 miles an hour.
And that's not. I mean, it's not like a hard gradient, but it's not.
It can be fairly sharp gradient in some cases. Like you can accelerate from 0 to 100 miles an hour within 1,000 feet.
Yeah.
And some of these balloons back in the day or even now, are like 300 feet tall.
That's crazy. So yeah, one end's gonna be pulled away, and the other end's still standing still, not knowing what's about to hit it.
Yeah, it's crack the whip with a payload.
quarter mil thickness. Interesting.
Jeez. From polyethylene. That's good. The Mylars and similar films being so brittle really had trouble with the turbulent whipping because it would so easily
just crack it.
Yeah, it's crack and just tear. Whereas the polyethylene has a little bit of ductility, a little springiness to take those massive shocks.
Yeah, especially at that temperature, because at that point you're up in the negative 40s, right?
Yeah.
We don't need to define Fahrenheit or Celsius though at that temp.
that is, I love that convenience. It's freaking cold. Both scales are the same. Strength members.
Anything colder is not really big deal.
Yeah. Strength members are nylon bonded to the polyethylene in a number of different grid patterns, depending on the particular strength requirements of the system.
So it's like a mesh with a
It
Sort
sounds
of.
like it. Let's go take a look and see. Since we have a reference to Figure 1, the test units in Figure 1 embody several different approaches to grid patterns. Some initial problems were encountered with delamination at altitude environmental temperatures of frickin' minus 90 degrees Fahrenheit. Handling temperatures in the regime of minus 110 degrees Fahrenheit are now easily satisfied. This sounds promising. Let's go find a picture. Well, look at that.
Interesting.
Those definitely look
Oh, so here's
super
your grid.
pressure. Yep. It's a big grid.
Yeah. So it's super pressure because not from like latex where it's holding it in uniformly. I'm picturing it uniformly, like a balloon,
Mm-hmm.
but it's holding it in with a net, basically.
Yeah, it's like capturing. Yeah, it's
Capturing it.
like you say. Yeah, it is forcibly restraining it.
That's interesting.
Looks like a mattress. That is interesting. So, and cylinder balloons, that's hard to make a cylinder mass efficient. And you've got to be really light mass to payload to go that high. That's impressive.
I guess the benefit there is you can just keep making it longer and longer and longer, right?
You can,
Or is there
but
balance?
geometry bites your ass eventually there because as you extend the cylinder, its volume increases slower than the mass of the plastic increases.
That's why we invented circles.
Yeah. Well, yeah, spheres. There's a really cool calculation that shows you that for every film and cylinder diameter, there is a length of balloon of that material that cannot lift itself off the ground. And you go shorter than that, and you start to be able to lift more and more and more payload. Is that not crazy?
Yeah. That is interesting. Yeah, it looks like they bundle it. It's bundled at the bottom. It's probably sealed.
Yeah.
It'll eventually fill all the way down to the base. That middle one looks like actually is.
It must be for low altitude, yeah, because I'd imagine you'd have to have it. Well, they seem to be running them at high pressure. I guess we'll know. I mean, if it can withstand insane pressures, you could have fairly decent volume inflated at the ground.
Yeah, or just you fill it completely and then vent as you go up.
Oh, maybe. Yeah, that's true. That's like we were going to do in the White Star project.
Exactly. Yeah. Yes. How complicated can we make it?
Yes.
A valve on the balloon.
Yes. Okay, so we were here at
grid patterns. Yeah.
It is found that conventional techniques for quality control do not apply because the material is relatively fragile. Thus, the handling processes require special attention and seaming techniques are unique. These factors have received developmental efforts over the past 2 years with the resulting low weight, high strength fabric and compatible processing. It is interesting to note that originally, when SSS first started making the very light fabrics, it was done by hand on a loom with weavers passing the shuttle back and forth. This, of course, was a very laborious process. About the time a crew of Navajo Indian rug weavers was engaged, Mr. Tom Kelly said we were violating the child labor laws. Oh my God.
Whoops.
Did I tell you these old papers had personality?
Yeah.
And it would have to be done a different way.
They weren't just going to well, maybe we should just leave that out. Nope. Or it's public record. We're going to put it in there.
Yeah, it's too good to leave out. Oh, I love these guys. Sea Space Systems, going to have to look for more by them. Consequently, during the summer of '63, SSS completed the development of a prototype fabrication machine to effect the weaving automatically and ethically. The machine not only weaves, but it also laminates and cures in one continuous process.
and it makes julienne fries.
Yes, exactly. But wait, there's more. Turning to the potential of this fabric, the drive to date has been directed primarily toward very high altitude flights. If lower flight altitudes are desired, say 100,000 feet or less, and the job can be done with a polyethylene or neoprene type balloon, MERFAB does not appear to have application. However, if altitudes in excess of 100,000 feet are required, and in particular altitudes of 150,000 feet, then MERFAB is strongly indicated. For future reference, in the case of superpressure balloons and/or load carriers, it appears that the material has excellent potential. So it sounds like they weren't actually designing it expressly for superpressure with this.
Yeah, because superpressure balloons and or load carriers. So load carriers would imply what?
I don't know.
Zero pressure? Why would they make that distinction?
Yeah, load carriers. Superpressure and/or load carriers. I don't know. Load carriers. I suppose the typical design of the big zero pressure balloons is to have the weak polyethylene in the vertical gore strips with heavy duty load tapes or ropes in the valleys of the gores to actually carry the load, to transmit the load from the payload amongst the entire length of gore. So I suppose if you considered that load to be, if you wanted to instead transmit that load to a net, like this fabric, maybe?
Yeah. That way you're not putting all your load in a small area of thin film. That's definitely not going to hold it.
Yeah. A first step in using MERFAB for an operational application, it was felt that a modest case should be attempted involving a sounding balloon which would carry a small payload to an altitude of 150,000 feet. This usage means generating the capability of built-in gas containment with a large expansion ratio. By way of visualization, if one starts with 1 cubic foot of lifting gas at sea level, it will expand to well over 350 cubic feet by the time it gets to the altitudes of interest. MERFAB can represent this type of volumetric change capacity. Now, for this first step, what are the specifics that would be desirable? Certainly, there are a number of scientists and military personnel who would be interested in carrying scientific payloads to 150,000 feet. As a consequence, it was determined that a reasonably small scientific payload to that altitude would be commensurate with a radio sound. How convenient.
Magic.
Off-the-shelf telemetering and locating. Thus, a design point of 150,000 feet with a 3.5 pound payload. They apparently had pretty tubby radio sondes back then.
Yeah, right. I was just thinking. Long until the days of lithium.
Yeah, probably vacuum tube powered. I literally have seen diagrams of vacuum tube radio sondes, like clearly high dollar. Certainly, weather considerations were paramount, including the accommodation of temperatures in the equatorial regions to minus 90 degrees Fahrenheit.
Does that mean that in the equatorial regions the high altitudes are actually cooler?
Yes, they are. That is something I learned in my time at Loon. The coldest your balloon will ever get on the planet is over a thunderstorm on the equator.
Interesting.
It's so bizarre. And the reason is that your balloon is heated from, solar and everything, basically a sphere in all directions. The infrared radiation coming into your balloon and payload is what heats it. Yeah. Pretty much agnostic of the air temperature. And your Earth radiation heat is a big factor, it turns out, in the balloon's temperature, both night and day. And
that's your black. Is that your black body radiation type stuff?
Exactly, yes. You consider whatever you see below you as a black body at the temperature that thing is, which perfectly segues into the fact that the temperature of the ground, or whatever's in between you and the ground, blocking the ground, is what infrared energy is going to be hitting your vehicle. And so if you have a cloud deck at 20,000 feet where it's minus 10 degrees Celsius, well, from horizon to horizon, then that's your average incoming radiation temperature. Most of the Earth doesn't have that kind of cloud decking, and if it does, most clouds are 20,000 foot or below, where it's moderately warm. However, in the equator, there's pretty consistent thunderstorms that rise up to the top of the troposphere and spread out into huge anvils, which are very close to your balloon, which means you get a very wide horizon of ice crystals that are 90 below zero.
That's sucking blocking all your heat.
Blocking all your heat. So all of the infrared radiation you get is almost nothing, basically 90 below. And at night, that's serious danger. That determines your operational balloon design. Like Loon's balloons, they had to make a decision. Do we avoid flying ever in this situation? Because the initial design of the balloon collapsed in that situation. Like the helium contracted so much that it went zero pressure and descended all night until it landed. Super pressure was gone. Or to design in like the ability to withstand that low of a pressure, that means you have to
much more
have a wider pressure range, like a higher max pressure to accommodate when you're flying over the Sahara. So that's
crazy.
It's really crazy. I love it. But you're right, you caught it.
And also the crazy thing is, how did they know in the 60s that that's how cold it was up there? On the equator.
They did a lot of balloon flying. We'll have to look at some more papers. There's so much information. Like they were voraciously throwing shit in the stratosphere. Like they were dying to know this stuff.
It's just amazing. Now it's all just like common knowledge, right?
Yeah, it's just a lookup. Yeah.
You just look it up, But back then it's kind of like, well, I don't know how cold it gets over there. Why is it colder the further south we get? I don't know. Let's throw a rocket up there and check it out.
Exactly. Yeah. Like one of the things I stumbled on was, we have defined the standard atmosphere tables. And these days, that's typically from 1976, the 1976 standard atmosphere table. And it goes beyond just showing you the curve of temperature versus altitude, but it also will define like typical regional hemispherical patterns for seasons and wind patterns and stuff like that. And in the 50s and 60s, like they went through several standard atmospheres. Like there were updates and fixes, and like that was when they were figuring it out. Like they had to correct the standard atmosphere to match better what they were finding.
That's crazy. It's impressive.
It is. I love it. It's the frontiers of scientific discovery of the atmosphere.
And of course, we ran out of things really to study, so now we're studying other planets' atmospheres.
Exactly.
I mean, there's never anything. We're not running out, but all right, well, we'll figure this one out. Let's go to the next planet.
Oh yeah. We'll have to look at the Venus balloon sometime. I've got a lot of papers.
Like Mars with such a thin atmosphere, is balloons even a feasible thing?
Yeah, I've got some papers on that, and it's very, very iffy. You're very fine line. Like, yeah. It's the same problem of getting to like 150,000 feet. You have a massive balloon that is gossamer and carries hardly any payload, and that's Mars. So you got to get that to Mars, then inflate it without tearing it, and then
launched by one man bot.
And then it can't fly at night. Like some of these papers say there's just not going to be enough heat. Like it's going to land at night because the solar input is going to be required.
You're not going to get that high because it's not that high to begin with.
Exactly.
Yeah, you go up high enough. So
it's a problem I suspect will wait for humans to go up there and tinker on balloons themselves. I don't think robots are going to pull that off. Or anyway, maybe we'll send a starship up there full of a balloon.
Yeah, or a helicopter. Someday they'll send a helicopter.
Yes, someday in the far future.
Far future.
Yes.
Weeks.
Yeah, can't wait to see that fly. Okay, so in order to stand strong wind shears in transit of the tropopause, that's the top of the troposphere and the bottom of the stratosphere, the design should have a large degree of structural capacity. So strong. Lastly, there was a strong desire to create a balloon that had launching ease for the untrained user. Oh, it's always nice, but sometimes a tough goal to meet. Yeah, users can be pretty untrained. In reference to previous balloon history, it is a well-established fact that balloon launching is quite a problem. Well, they're not pulling any punches here.
No.
I love this paper. I've never read it before. I'm glad you picked it. Thus, one of the major objectives was to provide a balloon that a scientist could take in the back of his truck or station wagon, or her.
Station
wagon. Yes.
His wood-paneled station wagon.
His science wagon.
Yeah.
Quickly set it up and launch by pulling a lever. Balloons by lever. It never occurred to me. That's brilliant. We should do that.
Not button. A lever.
A lever. I like the idea of a big, giant 3-foot lever mounted to the side of a station wagon.
Pull it.
His efforts, or her efforts, then would not be expended on the support train for the balloon or launching equipment, but rather they could concern themselves primarily with the scientific experiment, and they would be happy. Thus, the design must generate a launching technique that can accommodate a reasonable amount of wind, and has a flexible mobile launching capacity and can be launched by one person if necessary. I mean, that's great. I would love that for all kinds of balloon launches. Like, just, sure, do that.
Yeah.
Easy, I'm sure. So design of 150,000 feet and 3.5-pound payload is shown on the performance graph of Figure 2. The curve gives the general operational effectiveness of the MER-H3 design. If the balloon performance capability is examined, it is seen that a 12-pound payload can be lofted to 140,000 feet. That's impressive, actually.
Yeah.
So, Figure 2. That's a nice chart.
Yeah.
Simple. Yeah, okay, so I'm impressed that there was that much of a payload increase for only losing like 15,000 feet. Am I reading that right?
Yeah, that's what I'm getting.
140 to 155.
I mean, that last bit really hurts. You're losing a lot if you're getting that high, right?
Yeah, that's true. It is sort of like it starts to get exponential or asymptotic or whatever.
Yeah, it just drops off a cliff once you get up that high.
Yep. Yeah. Let's see.
You'll be naming individual, bits of atmosphere as they float by.
Yes, clawing past each one. So the MER-H3 balloon specifications are presented in Figure 3. The size of the sea level bubble is 10 feet in diameter, with the top 9.5 feet above the ground. Considering that there is probably, quite a long line associated with the payload in order to remove it from the airstream perturbations caused by the balloon, a launch train of approximately 200 feet results. Man, that's going to be a pain in the ass.
For one man.
Yeah, it should be noted that this is a fairly lengthy train for one man to launch. I should just keep reading. Figure 3. Yeah, so
But train 200. Well, they're basically
yeah, just
and okay, and
rehashing
they're,
it.
I was about to ask this question. They're assuming helium, right?
Yeah, I'm assuming. 79 feet in
It says
diameter. Is that 7.9? 7 point. I don't know. What do you think? 543.
no, it'd be 79 feet diameter is what it said up there in the paragraph
Oh
about.
yeah, yeah. I think you're right because you're putting 534 cubic feet in at ground level. We would like we put in like 300 into the White Star balloon, so it
Yeah,
would,
right.
and we were going only to 30,000 feet with that. So one man prep 30 minutes. Man, they are shooting for the moon on these operational specs here. G control. Like
Or
anti-gravity? What?
ground control?
Oh, maybe. Maybe. In operational launches, it has been demonstrated that one man can prepare and fill the balloon in approximately 30 minutes. Launching is effected by a lever release. The latter, in addition to creating one-person feasibility, is extremely effective in situations where the launch has to be coordinated with another operation, with release on the 0 countdown. For some cases, a reasonable amount of acceleration control has been included to limit the high G dynamic launch loads.
G. G being G.
G, yes, G. Single G. In terms of the balloon launching hardware, Figure 4 represents a complete system, including a radiosonde payload and associated parachute. The balloon is packed in a box, which sits in a foldable launcher. The gas requirement can be effected with 3 standard bottles. Figure 5 shows the launcher set up for operation and the balloon protective covering folded out. Let's go take a look at Figure 4. Well, they got their name in there anyway.
Space system.
Yes. Looks like we've got our lurking gas bottles here.
Ever present.
Oh, I recognize this. It's an old-fashioned radiosonde. It's hanging upside down, or it's sitting upside down. And what is this big-ass box? What is that? Oh, maybe that's what the balloon... Oh, they said the balloon was in the box in this photo, so that must be it.
Yeah. And it must unfold out of there, opens up, and just it's laid in there like a sheet, laid folded over on itself.
Up. Yeah.
Very carefully.
Yeah, I think we'll have to take the word for this picture's word for it. I can't figure this out.
Yeah.
Moving on. This
copies and copies and copies of photos.
You might find this tidbit of tech information interesting. I believe this and most of my documents came from the land of microfiche.
Ah, yep.
Which is essentially just a copy of a copy, but...
And limited resolution.
Yep, and limited dynamic range. It's a 1-bit operation, like a photocopy. Okay, so, oops, marking up these things. So, attention must be given to the protection of the balloon material because it cannot be handled in the conventional manner. It is relatively fragile, and if pulled with the fingers, stress concentrations can result with the possibility of gas leakage. Thus, the protective system is designed to prevent the user from actually grasping the balloon with their hand. Their grubby little fingers are prevented from touching.
Like touching a halogen bulb. Put coils on there. Pop goes the bulb.
The balloon is contained in its transportation box, with the balloon never emerging from the box until the actual launch. The section that is inflated for the initial bubble fill is protected by an outside sheath covering, which comes off after launch. In Figure 6, the bubble is fully inflated, ready to go. It should be noticed that the launcher has 2 arms in the front and 1 arm to the rear. This configuration allows orientation of the twin arms into the wind in such a way as to resist the wind forces. There is a tab arrangement to hold the bubble secure and shield the balloon from wind gusts. The taut bubble installation can sit in a reasonable amount of wind, then, with a person to the rear holding the payload on one hand, the balloon can be launched by pulling the release lever with the other. Launchings to date have been highly successful. Let's go take a look here. Bubble fully inflated, ready for launch.
You're basically, instead of having to chase the balloon, train downwind as it floats up, you're holding the balloon basically above the launch site and letting it go up, straight up, anchored.
I guess.
I don't know.
I wasn't. I did you catch like what's actually holding the balloon down? I
think it's just like a net or a cover.
Oh, okay, yeah, I think it is a cover. I was not processing. Like, looks like these are what is carrying the load, and that might be, like you're saying, might be
like a net or a sheave that covers the whole top of the balloon.
That would make sense. Yeah.
Then I guess you could. I don't know. I mean, I guess you're. If it's all folded and you have high winds, I'm just trying to picture how that would work. You got wind blowing everything, downwind.
Yeah, this.
So if you lose, it's going to want to go.
It's going to go downwind. Yeah. It looks like. Take a look at this. It looks like it's like a 3-legged. I'm picturing. Looks like a 3-legged stand that's laying on the ground. Each of these things are coming down to. Like a Y-shaped frame.
Yeah. If you if it was going up, but you limited how far over it could go, but still, it's going to drag it off. So I don't know. I'm trying to picture what that would do.
Yeah, after the release, like you say, if the wind takes it, that's problematic for that payload. Let's see, where did we leave off? We were down below the pictures.
Well, that one right above it.
Wait, this one.
Yeah. Launcher set for operation with the balloon protective covering folded out. Okay, so it's basically like laying there, waiting to be filled.
I guess. With
the balloon coming out of the protective box, and it's just going to hold on to it.
Oh, the protective cover that the balloon is shipped in might be that thing that it's actually anchored by.
Yeah. And so you fill it, and then I guess at that point you can release the whole thing all at once and just let it fly out of the box.
Yeah.
Going up and away, downwind, and the balloon just unfolds out of the box as it gets taken out.
Yes. Yep. Boy, that looks a lot like a jellyfish.
And then I guess and then that cover.
You think this is the cover here?
Yeah, it gets split or something.
Oh, you know what? Yeah, if the balloon expanded, I wonder if it just like pops it off like a little hat. That would be pretty cool. Let's see.
Falls to the side, and the balloon comes out. Yeah.
Yeah, like a cocoon or molting. So launchings have been highly successful. The maximum condition experienced in the lee of an inflation building has been a wind of 20 knots with gusts to 28. That is staggeringly high wind for a balloon launch. That's impressive. It is felt that the launch capability described above can go to even larger bubbles associated with 2 million cubic feet balloons, while still maintaining system portability. What are they talking about? I mean,
a few more tanks of helium,
Yeah, 2 million cubic feet. I mean, yes, I mean, I suppose if portability includes a shipping container, yeah,
Back when helium was plentiful and cheap.
exactly. Yeah, just bring your helium tanker along. Several launches are scheduled with 1.5 million cubic feet balloons carrying 25-pound payloads. Oh, wow, that's a lot of balloon for a little payload. Wow. Figure 7 shows the MERH-3 balloon just an instant after release. It is seen that the protective sheath has now cleared the launcher. It will be released after the balloon has ascended further. I think we were right. The balloon basically grows
Yeah,
out of it.
it just splits.
That's cool. I like that idea. Additional protection of the fabric during ascent trajectory is achieved by a system of reefing, which is removed progressively as the balloon goes to altitude.
Like a sail. So
Or parachute.
yes.
So yeah, so
So as
there's
it
little
split.
reef things here.
Yeah, interesting.
That's fascinating.
Well, that sure makes it a lot tidier to launch because now you just have this big long umbilical that flies out of the box.
So much better to launch. I like that. I wonder how they got those to trigger, because this is a great method for launching. Very clean and tidy.
Just like a rubber band or something. It wouldn't take much. And you wouldn't want it very strong.
But they
Not rubber band, but something that would split with minimal effort.
Like I'm learning. This is interesting. I'm learning stuff from this paper about launching that I think is relevant today. So the long length of the train is clearly visible. Flight progress to date can be summarized for a unit whose performance altitude was 146,000 feet in the following AEC press release. Near record altitudes for unmanned balloons were reached in test flights at Tonopah, Nevada test range, when one reached an altitude of 145,000 feet on October 4th. The previous NASA record of 148,000 was set by a U.S. Navy balloon in 1959. Designed to carry radiosondes, the balloons were tracked by radar to give wind observations and altitudes with 50-foot accuracy. Whoa. That's a lot. Weather data at these altitudes are used in studies of worldwide stratospheric fallout. Oh, nice. The balloons were designed and manufactured by Sea Space Systems of Torrance, California. Thin polyethylene plastic film is used to make them retain flexibility at temperatures as low as 112 degrees Fahrenheit below zero. In summary, the following accomplishments appear pertinent. 3 years of development work have achieved a light, strong fabric having potential for high-altitude flight, a launch technique exhibiting very desirable operational characteristics, and the MERH-3 balloon vehicle for carrying a 3.5-pound payload is considered to be off the shelf. Larger payloads to 12 pounds can be carried to 140,000 feet, and there is strong growth potential, holding promise for larger payloads. The end.
No. They didn't really talk about, besides just polyethylene, what actually makes that up. But they mentioned early on MERFAB, which is interesting.
Yeah, I'll have to dig further in. I'm very curious what happened to this miracle fabric that they apparently have invented.
Well, I'll send you a link because I did a search on MERFAB and Sea Space Systems, and there's a NASA technical report thing.
Excellent.
That talks about. Actually, it has really good drawings, I guess I should say.
Let's take a look at
that. That talks about like 30 plies of 0.10 mil polyethylene assembled into 15 MERFAB elements with 40 denier HT nylon fibers.
Denier, I think. I'm not sure. That's I know that's a term
Yeah.
from fabric. I don't know what it is though. Let's see.
This is a 400-page PDF, but it's
Good.
in great condition, high quality.
Oh, excellent. This would be great to add to my archive. Let me download this here. We'll just quick take a peek here. Yeah, it's taking its time to download. Well, that's cool.
I don't know if I lost your.
Yeah, it's
there
I accidentally started Chrome and it opened 1,000 tabs. I have now switched to Safari, which had one tab previously open, and it is ever so slowly downloading this PDF.
Interesting. That's a hefty PDF. It's got pictures in it and all sorts of stuff. Let me see what this actually was talking about. This is the development of I'm mispronouncing that. Cryogenic positive expulsion bladders. Beach Aircraft Corporation. That's funny.
That's curious.
Expulsion bladders. Cleveland, Ohio. Interesting. Man, it's like.
What's the title of that?
Here, actually, it's in text. I'll just I'll paste it to you. And here. Well, mostly.
Yeah. Positive expulsion bladders.
So it's Jeremy.
Bladders. It must be a big PDF. My it's still downloading.
It's big. Well, I don't know how big it was, but it's 400 pages and it's pretty good quality.
Excellent.
Let's see here. It was 62 meg.
My internet must just not be keeping up.
It looked like MERFAB was a sea space systems technology, is what it looks like.
Their trade name for their thing.
Right. And MERFAB. It's fabricated. And I think I found your other article, the ultra thin film balloons article, because it talks about MERFAB in there a lot too.
Yep, that's Cox and Sea Space. Yeah, I don't have this one.
Sure, I don't think this actually has anything to do with balloons. It's just they're good at making, I don't know what you would call it, balloons. But this is for something else.
Films.
They're maybe filling bladders up with really cold stuff.
Yeah, and obviously this film was developed for cold temperatures. It is a pretty PDF. Wow. Take a look at that here.
That's interesting. Actually, it looked like in that, I think it's the other article you have, the ultra thin film balloons actually has a picture of a 1.5 million cubic foot balloon inflated in the SSS launcher.
Really? All right, let's pull that one up here.
I think that's the same article you've got. I can see parts of it in Google. Actually, it looks like I can see the whole thing.
MERFAB.
Looks like it's on, let's see, page. Yeah, it's on page 116. That must be a big document. I'll send you the link to this because it might be a book instead,
The ultra-thin
not just
film.
a simple. Yeah, I don't know if this link will get you where you want, but that's interesting. That's interesting. That's
Is this the one?
that they were making stuff like that.
Oh, keep going.
No, I'm just looking at this. It's just amazing what they were doing in the 60s.
Yeah.
All these composite materials.
Totally.
And basically, that's what it is. It's a composite.
Yeah. You're right.
Balloon.
There we go. Okay, I've got the picture of the inflated in the launcher. 1.5 million cubic feet. Seems excessive.
If you want to haul a telescope up there or something, you know.
A 25-pound telescope. Oh, the language is chatty in this one too. Dr. Elliot, our neighbor at China Lake. Oh, we'll have to look at this one another time. Well,
yeah, that's a big PDF.
Well, this has been fun, Ted. I appreciate you dropping by.
Yeah, definitely. Definitely a learning experience.
Yeah.
And learn more about balloons than I probably ever will need to. But
yes.
fun learning stuff.
Well, let's do it again sometime.
Definitely.
All right. Take care. I'll talk to you later.
Yep. See ya.
Bye-bye.